In this video, I'll be presenting a simple LED circuit to introduce basic circuit concepts and circuit laws. The tools you'll need are a breadboard, a microbit with a breadboard adapter, a USB cable or battery for the microbit, jumper wires, a 220 ohm resistor, an LED of any color, and a multimeter. Our goal here is to use the microbit's power supply to light a single LED, as shown in this circuit diagram. This is what the completed circuit will look like. By following the steps in this video, we can safely build the circuit that lights the LED, and along the way we can discuss some of the basics of electronic circuits. If you are new to electronics, this very simple circuit will be your introduction to basic electronic circuit principles. The first thing to remember is that we never build any circuit while the power is connected. In our case, we must disconnect the battery and the USB cable from the microbit so that there is no voltage from its power supply going to the breadboard. It's fine to leave the microbit in the breadboard adapter, but we should only connect the battery or the USB cable to the microbit after we have built the circuit and we have also checked for any accidental miswiring. Now, these are the steps to build our LED circuit powered by the microbit. Step 1. Wire the voltage rails. The breadboard has voltage rails running along its entire length. One is usually colored red and has a plus sign, and the other is usually blue with a minus sign. We will be using the red for our 3-volt rail and blue for our ground or 0-volt rail. Add a short black jumper wire from the pin labeled G to the blue rail. Then add a short red jumper wire from the pin labeled 3 volts to the red rail. In order to help remember what wires go where, generally I prefer to use red jumper wires for direct connections to the 3-volt rail and black for direct connections to ground. It doesn't actually matter, this is just a convenience. Now we need to check that the rails are correctly wired, so we'll need to temporarily wire some test jumpers to the rails, while making sure that the free ends of the jumpers do not touch. If they do touch while the microbit is powered, there could be some damage to the microbit, so please be careful. We will use our multimeter set to DC voltage, with the black lead plugged into the common socket and the red lead into the volt-ohm socket. In my case, I will use the 20-volt DC range. Power on the microbit with either the USB cable or the battery, and then hold the 2 test leads to the test jumpers, and check that our voltage rails measure about 3 volts. See that I have held one jumper in each hand and pressed each test probe to the jumper with my fingers. Because the resistance across my body is many megaohms, the reading will still be reasonably accurate. Just remember to make sure that the ends of the test jumpers never touch each other. As soon as we have done this rail voltage check, we immediately power down the microbit and remove the test jumpers to make sure we can't do any damage as we continue the build. Next, we choose a 220 ohm resistor and check its resistance value by using the multimeter in resistance mode. Here I have put my multimeter into resistance mode in the 2k ohm range to read a 220 ohm resistor. When measuring the resistor, use 2 hands to press the test leads against the leads of the resistor. Insert both legs of the resistor into the breadboard, oriented along the length of the board. It doesn't matter which direction the resistor is connected, because it works the same both ways. Now add a red jumper wire from the 3-volt rail to one leg of the resistor. It helps to remember that a breadboard is internally constructed so that the holes are connected across the board in groups of 5 holes, like this. Now choose your LED. The most common type used in hobby electronics looks like this. Notice that it has one lead longer than the other. This longer lead must be connected to the positive voltage, and the shorter lead must be connected to the negative voltage. Unlike the resistor, the LED is polarized, meaning that it only allows current to flow in one direction. If you insert the LED against this polarization, there is no risk of damage to the circuit, but instead it will block the flow of current and it will not light up. Insert the long lead of the LED into the same line on the breadboard as the other end of the resistor. Then add a black jumper wire from the short end of the LED to the blue rail, and our circuit is complete. Next, we must check the circuit before powering on the microbit. Reconnect the test jumpers to the voltage rails. This time, instead of measuring the voltage, we will put our multimeter into resistance mode and check for a short circuit across the voltage rails. When the multimeter is in resistance mode, if a short circuit is detected, the display will show a 0 like this. Notice that I've touched the test probes together to show what a short circuit looks like on the display. If you see 0 ohms across the voltage rails, there is a mistake in the wiring and you'll need to carefully check your circuit to find and fix the short before powering on. Once you see a non-zero resistance across the rails, you can attach the battery or the USB cable to the microbit and see the LED light up. If everything worked as planned, then great, well done. Otherwise, you'll need to disconnect the power and carefully check your assembly again to look for mistakes. And remember, never work on your circuit with the power still connected. Congratulations on building your first electronic circuit. Now that we have built our circuit and it works, I'm going to introduce some basic circuit analysis that will form the foundation of all your electronic circuit knowledge. The first task is to measure the voltage drop across the LED. We use the term voltage drop whenever electrical energy is being converted to another form of energy. In the case of the LED, it converts electrical energy into light. It's tempting to simply use the long probes from the multimeter and touch on each lead of the LED, but in practice this is a bad idea, because it's incredibly easy to accidentally create a short circuit with the long metal probes and potentially damage something. So instead, with the power disconnected, add test jumpers across the LED and put your multimeter into voltage mode again, remembering to make sure that the bare ends of the test jumpers never touch. Reattach the power and take your measurement with the multimeter. When you are done, remember to remove the power followed by removing the test jumpers. Now I could have simply used the multimeter to measure the voltage drop across the resistor as well, but I'm going to do this the long way because it allows me to explain some important circuit analysis principles. But in practice, if I wanted to know the voltage drop across the resistor, I would simply use the multimeter and measure it directly. Now let's look at the circuit design in detail. This is a series circuit with 3 voltages: the source voltage Vs, the resistor voltage Vr, and the LED voltage VL. The relationship between them can be expressed mathematically by following a loop that matches the current flow like this. Our aim is to equate the voltage rises with the voltage drops in the loop. Our analysis always proceeds like this. As we go around the loop, we put each voltage rise on one side of an equation and each voltage drop on the other. The first voltage in our loop is the power supply, which adds electrical energy, so we put it on the rise side. Then we get to the resistor, which converts electrical energy into heat, so we put it on the drop side. And lastly, the LED, which converts electrical energy into light, so it goes with the drops. This gives us Vs equals Vr plus Vl. Rearranging to find Vr, the unknown, gives us which we get from subtracting Vl from each side. So in our case, with our measurements, we have Vr equals 2.97, which is the source voltage, minus the drop across the LED, which is 1.91 volts, giving us 1.06 volts across the resistor. Now the easiest way to determine the circuit current is to calculate the current through the resistor using Ohm's law. Because we have measured its resistance and calculated its voltage drop, we can determine the resistor's current using Ohm's law like this. Firstly, Ohm's law can be written as V equals IR. Then we rearrange the equation to put these knowns on one side and our unknown, the current, on the other. We get this form of Ohm's law by dividing both sides by R to give us I equals V on R. This then gives us 1.06 volts divided by 218 ohms, which equals 0.0048 and so on amperes, or about 5 milliamps. Since this is a single loop circuit, the current is the same everywhere in the loop, so we know the current through the LED is also 5 milliamps. Because this type of LED cannot handle more than about 20 milliamps, the function of this resistor is to limit the current through the LED to protect it from burning out. If the resistor was less than about 50 ohms, or there was no resistor at all, the resulting current through the LED would light it up briefly, then burn it out. So in this case we call the resistor a current limiting resistor, which is used to protect the LED from burning out. This resistor also controls the brightness of the LED, with higher resistance values making the LED dimmer and lower resistance making it brighter. Try this for yourself. Change the current limiting resistor in your circuit build to a different resistance. Just remember to always remove the power from the circuit before making any changes, and don't use a resistor that is less than 50 ohms for this circuit and type of LED to avoid burning it out. And if burning out LEDs excites anybody, there is a video I like by Afrotechmods showing exactly what happens to an LED in the absence of a current limiting resistor. Enjoy! I'll put the link to that video in the description.
I'm going to set the power supply to 7.5 volts, and I'm going to remove all current limits. Let's see what happens. So if you significantly exceed the LED's forward voltage rating, massive amounts of current will flow through the LED, and there's nothing to stop it from blowing itself up. Obviously, don't do this at home. It's actually possible for LEDs to explode, sending tiny chunks of plastic and metal flying at your face. You don't want to end up looking like this. Now you see why in my video on voltage, a 9-volt battery was enough to instantaneously kill an LED. There needs to be something to limit the amount of current to a safe value.
Now let's go through a summary of what we have learned by building this simple LED circuit. We learned to insert jumpers and components into a breadboard. We learned how to measure voltage and resistance with a multimeter. We learned that an LED converts electrical energy into light, and its brightness can be controlled by a current limiting resistor. We learned that we should never turn on the power to a circuit when building or making changes to it to avoid accidental short circuits. We also learned to avoid using the multimeter's probes directly on the circuit while it is powered, but instead to insert jumper wires as test probes, and to always make sure that the ends of the test jumpers never touch each other while the circuit is powered. We learned that we can calculate the total voltage around a series circuit loop by adding up the individual voltages. This introduces Kirchhoff's voltage law. We also learned to apply Ohm's law to a resistor to determine the current in a series loop circuit. And that's all for this lesson. I hope you learned something, and I hope you are ready to learn even more in the future. Thank you for watching. It's apparently traditional at this point in the video for the creator, myself, to beg you, the viewer, to click the like button and to also subscribe to my channel. So if you feel so inclined, that would be great. In addition, should you feel compelled to add a comment with some constructive advice for myself or for others, that would be much appreciated too. In any case, please have a wonderful day. Bye for now.